Good afternoon. We are going to learn about how to describe linear graph behavior, starting with domain and range, and going to other types of descriptors like boundedness, increasing, decreasing, intervals, and things like that. You are going to want graph paper for this. You will want a ruler for this. We will be doing a considerable amount of graphing. So grab your ruler, grab your graph paper, and let's dive in. Okay, Roman numeral 1, domain and range. Okay, we're going to draw a graph. The graph is f of x equals 2x plus 1. This is basically a line with slope. Okay, so draw yourself a pair of axes. And I'm going to color code this because I'm using the same grid for more than one line. So this crosses at 1. It's got a slope of 2. And there is our graph. Okay, so the domain of the graph, which is the set of all x values, you want to know what could x possibly be and land on the graph. Well, because of this arrow, your x values go infinitely left. Because of this arrow, your x values go infinitely right. So your domain is from negative infinity to positive infinity. Range. Range is the set of all y values. This arrow says that your y values go infinitely down. This arrow says y values go infinitely up. In fact, all lines with slope have a domain and range of negative infinity to positive infinity because they go infinitely in two directions. But what if we have a line that it does not have a slope? So I want you to draw a line at 3. Okay, this is example 2. This is the line x equals 3. So this is not going to have negative infinity to positive infinity for both domain and range. Well, let's look at it. For x values, this is the only x value there is 3. X is not 2 or 1. X is not 4 or 5. So we say that our domain is the set of all values including 3 only. That's how you show a single point. Now range, the y values, infinitely up, infinitely down, negative infinity to positive infinity. Vertical and horizontal lines only have one single value for either the domain or the range. All right, example 3. We're going to actually generate a domain, or sorry, generate a range. So let's say that you are given the domain of x is an element of the set containing -2, 0, and 1. This means that your x can only have 3 values. It cannot have any other values between them, only those 3 points. Given that the function g of x is equal to -3x plus 7, the question is, what is the range? What is the range? All right, so conceptually, something you need to keep in mind is that x always generates y. That's why we call x the independent variable and y the dependent variable, because y depends on x. So to figure out what the range is, we need to figure out what y value goes with these 3 individual x values. So let's find g of -2. That's -3 times -2 plus 7. Which is 6 plus 7 or 13. G of 0, substitute in the 0. -3 times 0 plus 7 is a 7. And G of 1, -3 times 1 plus 7 is a 4. So therefore, we can say that the range of this function is the set of all y values such that y is an element of the set containing 13, 7, and 4. If there are only 3 x values, there are only 3 y values in the range. Now, what does this actually look like? Well, graphically speaking, a function that consists of individual values will be a set of individual points. So -2, and I'm going to cheat just a little bit, -2 up 13 will be somewhere up there. 0, 7, and then 1, 4. This is a graph that has 3 elements of the domain, 3 elements of the range, and there's nothing in between, so you can't give an interval. You can only give a set. Okay, so that is domain and range of 3 different types of graph values. Now we're going to go on, Roman numeral 2. We're going to describe graph behavior, and we're going to expand this from domain and range to include other things. So first thing you need to know is about what we call boundedness. Boundedness refers to the y values and what they are doing. If something is bounded above, it means that, and we're just going to do a sketch here, it means that the graph turns around and goes the other way. It has a final point and it does not go any further. Bounded below, and I'm going to use a ruler because I totally cannot freehand lines. Okay, bounded below means it has a lowest point, like for example, an absolute value graph. It has a lowest point to it. And then you have what we just call bounded. Bounded means above and below. We just say bounded. So a bounded graph can be a lot of things, but one of the things it can be is a circle. It's bounded above and it's bounded below. It does not go to infinity in either direction. So that is boundedness. We'll call that A. B, we're going to do increasing and decreasing intervals. Okay, increasing and decreasing refer to slope. Increasing means the slope is going up. Decreasing means the slope is going down. To describe where this is happening, we use x intervals. And of course, we use interval notation to describe that. One thing that's important is if there is a boundary between an increasing and a decreasing, then that boundary gets a bracket. So just as a side note, if you have something going up and then down, and this is occurring at a 2, that 2 gets a bracket, whether you're expressing it as increasing or decreasing. All right, we're going to do an example graph, and we're going to describe these things. So draw yourself a pair of axes. And again, I'm going to color code this because I'm going to use the grid for more than one thing. Okay, so this is a graph that we're going to have a vertex at 2, -2, and it's going to cross at 0 and 1, 2, 3, 4, 0 and 4. And it's a parabola opening upward. All right, we're going to go through the list. Okay, so number 1, we want to know where the slope is. In a graph like this one, where it's curvy, then there is no slope. It has to be straight to have a slope. An absolute value graph will have slope. This one doesn't because it's curvy. Okay, number 2, we're going to describe boundedness. Boundedness, well, it does have a minimum value, so we would say this is bounded below because it has a boundary marker there. Okay, number 3. Increasing or decreasing intervals. So this has a negative slope. It's decreasing down to x equals 2. So we would say it's decreasing negative infinity to 2 inclusive. And then from here up, it's increasing. So we would say it is increasing from 2 inclusive up to positive infinity. Those are our increasing, decreasing intervals. Okay, number 4, domain. So domain is the set of all x values. These go infinitely left and infinitely right. So my domain is negative infinity to positive infinity. And then the last category is range. My y values start at -2 and go up. So we're going to do starting at exactly -2 inclusive up to positive infinity. That is our range. Okay, using the same grid, I'm going to change colors here. And we're just going to do a really simple line y equals x. It's the one that goes through the corners. This one's actually, and to some extent, it's easier, but it's so easy, it's hard. So let's practice. Okay, so number 1 is slope. This definitely has slope. So our slope is going to be positive. And it's positive from negative infinity to positive infinity. It never turns around. So you want to give the boundaries of the slope. Number 2, boundedness. Well, this is not bounded below because it keeps going. It's not bounded above. So we say this is unbounded. That's not a word that I gave you up above. Unbounded means it doesn't stop either top or bottom. Number 3, increasing or decreasing intervals. This whole thing is increasing because it's going up the whole time. It never drops down. So negative infinity to positive infinity is the interval where that's happening. Number 4, and we talked about this on the first page, number 4, domain and range are always in a line with slope, negative infinity to positive infinity. All lines with slope have domain and range negative infinity to positive infinity. Okay, number 3, I mean, Roman numeral 3. Okay, Roman numeral 3. This is kind of an add-on topic that I've had questions about. Graphing with intercepts. Okay, when you graph with intercepts, basically you need to find the x-intercept, which is some number comma 0, and you need to find the y-intercept, which is 0 comma some number. If the intercepts are far enough apart to get a decent line, you're done. If not, you need one more point. If your x or your y are fractional, you can't get a good line off of that. You need to get at least 2 more points that are whole numbers. So it's a lot like graphing a regular line. It's just you have to make a few adjustments to how you do your graph. Okay, so let's do an example. We're going to do f of x equals 4x minus 1. Okay, so to find the x-intercept, all x-intercepts have y equal to 0. So you set y equal to 0 and you solve. So here we go. 0 equals 4x minus 1. Add the 1 over. We have 1 equals 4x. Multiply by a fourth. You get x equals 1/4. So my x-intercept is 1/4 comma 0. Now my y-intercept. The y always has a 0 for the x, so you set x equal to 0 and solve for the y. All right, let's do that. y equals 4 times 0 minus 1. That's 0, so y is negative 1. My y-intercept is 0, negative 1. This also makes sense because this is slope-intercept form. The y-intercept is always that spare number right there. Now, we do have one fractional point. So I'm going to come down here and graph, or start to graph. So we're going to need to calculate at least one other point to get a decent graph off this. So 1/4 0 would be something like right there. Not a great point. And then 0, negative 1. So we have two issues. One point is bad. The other one is too close anyway. So we really do need two extra points. So I want to pick something that's going to be out here. 2, 3, 4. 1, 2, 3. Like 3. So I'm going to set x equal to 3, which means that y equals 4 times 3 minus 1, which is 11. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's way up there. Maybe not out that far. 3, 11. And then I need one on the left. I'm going to do x equals negative 2. So y is 4 times negative 2 minus 1. Negative 8 minus 1 is negative 9. So 2 to the left and down. 1, 2, 3, 4, 5, 6, 7, 8, 9. There it is. Negative 2, negative 9. So put your ruler across, draw your line, don't forget your arrowheads. So those are your basic rules for graphing with intercepts. If you have good intercepts that are far enough apart, like here and here, you don't need any extra points. You can just draw the line. Naturally, when in doubt, add points. You can never have too many points when you're graphing. Okay. All right, I think that concludes the notes for today. I hope that was helpful. And we're going to be probably doing some practice problems during class on this topic in case you have additional questions. Have a good afternoon.